Hey, this is the 8.2 AP Statistics talking about confidence intervals dealing with specifically to proportions. I'm going to do this one into two different videos, so this will be the first part of two. So basically, if we think about anytime we're dealing with proportions, as with last chapter with sampling distributions, there were these conditions that needed to be met, and the same exact ones apply here. Pretty much anytime you're dealing with any sort of sampling and inference, you need to have a random sample, so that needs to be kind of given to you in the wording in the problem. Um, the sampling distribution needs to be approximately normal. So if we go way back, I know it's been a while, that goes back to kind of the binomial, where the n times p greater than or equal to 10, and n times q, or n times 1 minus p greater than or equal to 10. That's again what makes the binomial distribution be normal, and this one's based basically on the binomial. But the issue here is, will we know n and p? Okay, so what are n and p? So n, of course, is sample size, and that should be given to you. Are we going to know p? Okay, think about p is the parameter. It's the population's proportion, right? And if we think about last chapter, we knew p. They would say, suppose the population percentage is 0.6 or whatever. In this chapter, we don't know p. Remember, we're trying to estimate p. We're trying to come up with an interval to estimate p. So in this case, we don't know p. So how are we going to check that condition? What do you think would be something we could use in place of p? Yep, p hat, right? We're going to be able to get sample data. So what we're going to do is just throw a little hat on those up there. When you check your conditions, you have to use p hat, because again, we don't know p. So there's, we can't just be stuck from the beginning, otherwise we couldn't do anything. So just use p hat in place of p, and we'll see a little more of that in a little bit. The other one, if you remember for the standard deviation formula, that population, this is to kind of have independence. We need to have a population at least 10 times the sample size, at least 10n, if we're sampling without replacement, which is almost always the case. Okay, so again, if it's been a while, just refresh on those. They're the exact same pretty much as sampling distribution. Okay, so if we wanted to create a confidence interval for some p, some population proportion, we would have to, like we said, we would have to obtain a sample proportion. Okay, and we will call that p hat, so just a nice little sample value, a statistic. And then what we would do, if you think about how everything is kind of spread out again, remember the one condition was about having normalness, and this is why. So again, we would know if this was the sampling distribution, if all the p hats were in here, we of course know that p would be at the center, the population value would be at the center. And we should know, going back to this empirical rule, that 95% of all the p hats should be within 2 standard deviations of p. So on here, either within this blue or in this purple shaded section, that's where 95% of all the p hats should be. Okay, there's going to be some in the green and then very few out past the green, but 95% of the time, each sample proportion should be, within 2 standard deviations of the true center here, p. So that tells, if we think about it the other way, 95% of the time, p will be within 2 standard deviations of p hat. Okay, and you need to think about, in this case, we're only going to know p hat. So our p hat might be here or something, or maybe our p hat is down here, or maybe it's real close to p. But 95% of the time, wherever our p hat ends up, it should be within 2 standard deviations of this p, the center here. Okay, so that's kind of the thought. So let's think about this now. For a confidence interval, we talked about in the first section, it's going to be a point estimate, which is your p hat, plus or minus, we got to talk about this critical value, and then times the standard deviation. All this stuff after the plus or minus becomes your margin of error, we'll see. Okay, so the point estimate again, from the sample, p hat, when we're dealing with proportions. The critical value, it deals with the number of standard deviations, which is basically a Z-score, right? And we call it Z star, okay, because it's like a special Z. So we'll talk more about that in just a minute. And then what's the standard deviation for proportions going back? Yep, square root of p times 1 minus p over n. Okay, so that goes back to the sampling distribution formulas. But again, p is, we don't know p, right? So we got to make use of something we do know. So here's another time we have to use p hat in the standard deviation formula. Okay, remember, it was also used to check the conditions a few minutes ago. So pretty much anytime when you're doing these and it asks for p, if you don't know p, you have to use p hat. All right, so let's talk about this z-star value. What is it? Okay, so it depends on how confident you need to be. Okay, when we were talking about 95% of the time, we were talking roughly 2 standard deviations away. We're going to see how that kind of fits in. Here's kind of a way to find these. It's basically the z-score that's going to contain the middle blank percent. So whatever confidence level you're dealing with, um, that's going to be what we're going to use to find this z-star. So let's fill in this little table, and we're going to get 3 z-stars over here. And these are, like I said in the first section, these are the 3 common confidence levels, but I'll show you the way you can find the z-star for any level you want. Okay, so if we think about a normal curve, if we want 90% of the area to be, shaded in each tail, think about it, we have 100% total, I have 90% in the middle, so that means each tail would have 5%, right? 5%, like, let me go back. So imagine if the purple and the blue was 90%, that would mean the green would have to have 5% and 5% to make the whole be 100%. That's what I'm talking about, the tails out here, this green area. So for a 90% confidence level, we have 5% in each tail. So the z-score, what would be the z-score up there? Okay, we'll talk in just a second. If we wanted 95% confidence level, so we only have 5% not included, right? So 2.5% would be in each of the 2 tails. Okay, if we want 99% included in the middle, that means we only have 1% left over. Some in the right tail, some in the left tail, so we have 0.5%. Okay, so let's get these z-scores of this value. If we think about the inverse normal, that's how we kind of get a z-score of something. It's always the area below the value and then 0, 1 for a standardized z-score. So for this first one here, if we have 90% in the middle and we have 0.05 in each tail, so imagine, let me try and draw this here. I'm at home, so I don't have my nice smartboard, but we can do our best here. So let's say, let's see what we can do here. Let's say here's our normal curve. So this is not going to look very pretty, but I'm going to have to use the mouse. So let's say we had 90% in the middle, right? From there to there is 90%. Okay, and we said that basically then that left 5% in the tails, in each tail, right? In that little tail, 0.05. I guess I could have typed these, but and then in that tail, 0.05 as well, right? So what the z star is, it's actually going to be the z-score of this value right here. So basically, how many standard deviations is that? If this is your mean, what would that z-score have to be right there? That's going to be what we're calling z-star. It's always the upper level with 5% or whatever the confidence level is in the middle, and then you have a certain amount in the tail. So the way we do that is inverse norm, and if you think about how much area is below this value, right, it's the 90 plus 0.05, so it's 0.95 is the area below. So we're going to go to our calculators, and we're going to do a little inverse norm. So where are we at? Second distribution, inverse norm. Area below, we said this time, is 0.95. And since it's a standardized normal curve, 0 is the mean and 1 is the standard deviation. Okay, and this is going to give us a z-star value of 1.644. Okay, so that's actually our first one here, and it's we actually rounded up to 1.645. Okay, if we did the same kind of thing for a 95%, I think the area below would be the 95% in the middle plus the left tail here, so it would actually be 95 plus 0.025, so it would be 97.5. That would be the area below, and that one gives us around a 1.96. Okay, and notice that's the one we kind of said from the very beginning. Remember, 95% of the time we said is 2 standard deviations away. It's actually 1.96. They kind of just use 2 as an approximate, but the 1.96 is what we're going to use for z-star, and we'll go over some of this. I know this is kind of weird, but basically these 3 z-stars here are going to be 3 that you're just going to know. You're not going to really need to go through that process we just did. I just want to show you where they come from. But let's kind of see how we use them and what they do. The last one, of course, if you see the 99%, you'd have to go about 2.576 standard deviations to get 99% of the values. Okay, so let's take a look at an example. Here's a nice example. Oh, that ghost coming out here. Scary stuff, scary stuff. All right, let's say a poll found that 38% of a random sample of 1,012 adults said that they believe in ghosts. Okay, so that 38% is from a poll. It's from a sample, right? That is a statistic. p hat. We want to come up with a 95% confidence interval for the true proportion of adults who believe in ghosts. Okay, so let's think about this. We got to check our assumptions. Do we have everything we need? Do we have a normal distribution? Okay, I think we do. If we were to check there's p hat, so 0.38 times n times p, bigger than 10, right? And then 1012 times 1 minus p, also going to be bigger than 10, so make sure we check those. Make sure we do our random condition that they gave us that up here, and is the population at least 10n, so we're going to have to assume that if our sample is 1012, I would assume there's at least more than 10,120 adults in the whole population, so that one would kind of have to be assumed. All right, so let's think about that. We have our p hat, we have our confidence level, 95%. Okay, so that means we're going to use that z star. Remember, 95% is right around 2 standard deviations. It's technically 1.96. So here's going to be our setup here. Okay, here's the formula. We start to get this interval, right? Our estimate was 0.38. We're adding and subtracting 1.96 standard deviations. Okay, that's really what this is. The z star is how many standard deviations. And then this is just the standard deviation formula here for proportions. P times Q over N, and the square root of that whole thing. Okay, so this 1.96 times that square root is going to give us a margin of error. We're going to get a final answer of rounded between 0.35 and 0.41. So our conclusion would be we are 95% confident that the true proportion of adults who believe in ghosts is between 0.35 and 0.41. Okay, notice the 38% is dead center in that interval, right? We just added and subtracted. It looked like the margin of error, and this turned out to be about 3%. Right, because we went from 38, we went up to 41, and from 38 we went down to 35. Okay, so that's all we're saying. We're 95% confident the true P would be in between those values. Okay, so what would be the only change here if we needed to be 99% confident? Let's say instead of 95, I said I need to be more confident. Okay, the only thing that would change, if you think about looking at the formula, the p hat, that our estimate's still 0.38, the standard deviation is still the square root of p times q over n. It's just we would need to make the z star be larger because 99% is more than 2 standard deviations. Okay, the z star for 99% was 2.576. So that would just go in place of the 1.96, and we would do the exact same calculation. And if you want to just verify your calculations, it would create an interval from 34% to 41.8. So it's a little wider interval, but that's what had to happen for us to be more confident. We wanted 99% confidence. Okay, so for a little practice on page 496, you guys can give this a look, numbers 27 through 33 odd, and we will pick up the rest of the section in the next video.